Okay, so day 5, second derivative test. First, recall the first derivative test, and that's the formal name to how we determined relative extrema. We found the critical numbers of the function. We set those critical numbers on a number line, plugged them back into the first derivative, and then did a sign analysis. If the first derivative switched from positive to negative, a possible relative maximum occurred at that value. Where the derivative switched from negative to positive, a possible relative minimum occurred at that value. And if there was no sign change, no extrema occurred at that critical number. So remember critical numbers. We found them by determining where the derivative equals 0 or the derivative does not exist. Okay, if we had extrema, where did they occur? We would take that critical number and plug it back into the function. Okay, so again, the goal of this chapter, what do the derivatives tell us about the graph of the function, the original? So wherever the critical number occurred, we would plug it back into the function to determine what the relative max or min was. So the second derivative test will be another way that we can determine relative extrema. With any theorem we study, certain conditions have to be met. Let f be a function such that the derivative at c is equal to 0. And the second derivative has to exist on the interval containing c. If the derivative equals 0, what does this represent graphically? There's a horizontal tangent line at the value that's making the derivative 0. So at this x value we're calling c, the derivative is equal to 0, and therefore the function would have a horizontal tangent line. Alright, so the second derivative test. If the second derivative at c is positive, think about what a positive second derivative shows us. We would be on a concave up interval. So at the point where a horizontal tangent line exists on a concave up interval, that point would be a relative minimum. Where does it occur? At whatever the value of x is, and then we plug that value back into the original function. If the second derivative is negative at that value of c, negative second derivative tells us function is concave down on that interval. So at the point where a horizontal tangent line occurs on a concave down interval, a relative max would occur. And where do these come from? Remember, the y values always come from the original function. If the second derivative equals 0 at c, the test fails. And to determine if relative extrema occurs there, you would have to go back to the first derivative and compare the signs to the left and the right of the critical number. Use the second derivative test to determine any relative extrema. So first derivative, negative 4x cubed plus 12x squared plus 16x. So second derivative test. Find where the derivative equals 0, and then plug those values into the second derivative. So it's a limited view, all right? We're not testing the conditions where the derivative doesn't exist. All right, dividing out a negative 4x, we'd be left with x squared minus 3x minus 4. Factoring the function, we get 3 critical values. Alright, now let's find the second derivative. Negative 12x squared plus 24x plus 16. Now what we do, into the second derivative, replace these 3 numbers, because these 3 numbers are the values that's making the derivative equal to 0. So the second derivative at 0, substituting that in, the second derivative is positive, therefore a relative minimum occurs at 0, 0. And the y coordinate comes from plugging 0 back into the original function. The second derivative at positive 4. So negative 12 times 16 plus 24 times 4 plus 16. This would give us a negative value, and therefore a relative max would occur at the point 4, comma, plugging 4 back into the function. You can verify that the y coordinate is 120. Plugging negative 1 into the function, negative 12 minus 24 plus 16. This value would also be negative, and therefore another relative maximum would occur at the point negative 1. Plugging negative 1 back into the function, we get a y value of positive 3. And that's it. Determine where the derivative equals 0. Plug those values into the second derivative, and then the sign of the second derivative determines the extrema. Positive second derivative, concave up, therefore a relative min occurs. Second derivative negative, function is concave down, therefore a relative maximum would occur. You cannot use this theorem, though, if you're not first finding where the derivative equals 0. First derivative using the quotient rule, bottom times the derivative of the top, minus top times the derivative of the bottom, all over bottom squared, x minus 1. So this simplifies to negative 1 over x minus 1 squared. So in an attempt to find where the derivative equals 0, there's no conditions where the derivative equals 0. So the second derivative test does not apply. And sometimes it's as simple as answering a question like that. Okay, first derivative. If you want to rewrite this as quantity x squared plus 1 to the 1/2 power, using the power rule first, and then using the chain rule, times 2x. Okay, first derivative is equal to 0 when the numerator is 0, so when x is equal to 0. Now to find the second derivative, I would apply the quotient rule. Bottom times the derivative of the top, minus top times the derivative of the bottom. All over bottom squared. Now what I talked about on the video with the classwork solutions from when we were determining increasing and decreasing, the greatest common factor here would be x squared plus 1 to the negative 1/2. So all of the terms have an x squared plus 1. So if we factor out the x squared plus 1 to the 1/2, it would leave us with x squared plus 1 minus x squared, and then all over x squared plus 1 in the denominator. 1 minus negative 1/2 would give us 3/2 here. X squareds cancel, so our second derivative is 1 all over x squared plus 1 to the 3/2. If we were to plug 0 into the second derivative, because that's the value that made the first derivative 0, it'll be a positive answer. Therefore, the function is concave up, and a relative minimum would occur at the point 0, 1. And the y value comes from plugging 0 back into the original. All right. of x, 2 cosine x, minus sine 2x times 2. So using the chain rule here, derivative of cosine is negative sine, derivative of 2x is 2. Finding where the derivative equals 0. So I'm going to rewrite sine 2x as 2 sine x cosine x. And you can verify that property by splitting 2x into x plus x and then using one of our expansions from chapter 1. So 2 cosine x minus 2 times 2 sine x cosine x. Okay, now what do both terms have in common? A 2 cosine x. Dividing that out of each term, we'd be left with 1 minus 2 sine x. Setting each factor equal to 0. Cosine is equal to 0. And x equals pi over 2, or 3 pi over 2. Sine x equals positive 1/2 at pi over 6 and 5 pi over 6. Okay, so derivative is 0. Now we have 4 values to plug into the second derivative. So, going back to our first derivative in terms of sine and cosine, second derivative, negative 2 sine x minus 2, derivative of sine is positive cosine, derivative of 2x is 2. Plugging in pi over 2. Sine of pi over 2 is positive 1. 2 times pi over 2, however, gives us cosine of pi. Negative 2 plus 4. Positive second derivative, concave up. Therefore, a relative minimum occurs at pi over 2. Plugging 3 pi over 2 into the second derivative. Oops, sorry. This is f double prime. Negative 2. Sine of 3 pi over 2 is negative 1 minus 4 times the cosine. 2 times 3 pi over 2 would be 3 pi. 3 pi's, it's at the same spot as pi on the unit circle. So we have 2 plus 4. So this also is a positive second derivative, and therefore a relative minimum. Second derivative at pi over 6. Negative 2. Sine of pi over 6 is positive 1/2. Minus 4 times the cosine. 2 times pi over 6 is pi over 3. Negative 1. Minus 4 times cosine of pi over 3 is 1/2. So that second derivative will be negative, and therefore a relative max will occur at pi over 6. And the second derivative at 5 pi over 6. Negative 2. Sine is also positive in the second quadrant. Minus 4 times the cosine. 2 times 5 pi over 6 would give us 5 pi over 3. That's a fourth quadrant angle. So the cosine is positive 1/2 in the fourth quadrant as well. Also a negative second derivative, and therefore a relative max also occurs at 5 pi over 6. So in the essence of time, find the y coordinates of the relative extrema.